we started the last unit by thinking about what happens when you put an inductor in a circuit. So we had a battery and a switch and a resistor and an inductor. And we talked about when you close the switch, current will flow, current will create a magnetic field in the inductor. That magnetic field increases in time, so Faraday's law would predict a back EMF. And we thought about how that will affect the circuit. So now we really just want to do this mathematically. So let's label that R, let's label this L, some inductor with inductance L. And the way to do it mathematically is Kirchhoff's loop rule. Right? So we've done this for just simple resistive circuits. We've done it for RC circuits where you have a resistor and a capacitor. Now let's do it for what we're talking about now, which is RL circuits, resistor, inductor. Okay, well, Kirchhoff would say start here, go around the circuit, and all the delta V's should add up to 0, right? So if we go from here to here, that's low to high, so that's EMF of the battery. And then we can assume the current's going to go that way, we're looping that way, and that means this would be the high side of the resistor and the low side if the current flows that way, so it's minus IR. Like that. And then we know this is going to be a back EMF, so we would say minus L di dt. And you get back to here, back to 0. So that is Kirchhoff's loop rule for the RL circuit. And it's wrong. You should not do this. A big no. No. No, no, no. Most books do this, but it is not correct. Okay? This is completely wrong. You can't apply Kirchhoff's loop rule to this kind of a circuit. Let's think about what is Kirchhoff's loop rule really saying. It's really saying that the integral around a closed loop of E dot dl equals 0. And that's true in electrostatics. We know that the electrostatic field is conservative. If you have a charge here making a big field and you start here and you move around and you go back to here, the same place, the potential difference should be 0, right? Because the potential is well defined with a constant value everywhere in space. However, this is not true when you have currents changing in time, especially when you have inductors. And you always have a little bit of inductance, right? The circuit itself is a loop, right? So really any time the current changes, you're going to have some inductance. Now you have a much bigger inductance if you actually put an inductor there. So what we got to do is do this the right way. Okay, so let's think about the right way to do this. Let's try this again. Okay, RL circuit or LR circuit, same thing. Here we still have a battery. It still has an EMF. We still have a switch. We still have a resistor. And we still have an inductor. And we still want to analyze it mathematically. But we're not going to use Kirchhoff's loop rule because it's an approximation. What we want to use is something that is a property of the universe that is not an approximation. So that something is Faraday's law. Faraday's law tells us, has that same term in it. The integral of E dot dl equals minus d phi b dt. Right? This is the EMF generated in Faraday's law, and this is the rate of change of the magnetic flux through a loop. So for Faraday's law, we got to define this loop. Right? So what we say is the loop for the circuit is the loop that goes down the middle of this wire. Right? The switch is closed. Go through the wire. We go through the resistor, right? And we go through the wire that makes up this coil. So literally the circuit is the loop, like that. If I were going to, I could give it hatch marks like that. Right? There's our loop. And when you look at it, you might say, are we including the B field or not in this loop? It's a little bit, maybe we are. Well, it's very hard to visualize, but if you take a coil and you define it as part of a loop and think about what was really making the inside of the coil, or what's really making the surface that you're defining, it actually does go and include, in a way that I'm not going to draw very well, the part inside the coil. So my point is, the magnetic field created inside the coil will penetrate this loop, okay? If you work it out, or if you get a coil and dip it in a soap film and pull it up, you get this weird spiral shape, and the field does penetrate the spiral shape. So we are including in our circle the d phi b dt that's inside the inductor. It's in there, okay? Okay, so we want to do Faraday's law, and we don't want to think about Kirchhoff's loop rule, but I will allow us to think about the potential differences a little bit. So all I'm going to do is put the negative sign over here, right? Minus the integral around the loop of E dot dl, and then get rid of that minus sign is d phi b dt, right? Faraday's law, okay. And now you can see this is the definition of the potential difference. So I did this so we can say, okay, if we go around the loop and we go across the battery, what do we get? Well, just like in Kirchhoff analysis, we get the EMF. Right? The electric field in the battery, if this is positive and negative, points down, and we're walking against it, so that's negative. E dot dl is negative, but then this comes out negative. We get the EMF. Right? And we're walking through the wire, walking through the wire, walking through the wire. Nothing happens here. There's no field. Potential's constant. And then here, with a resistor, you get an electric field in the resistor pointing that way, right? And the current, we're assuming, is going that way. So that's minus IR. So similar term to Kirchhoff analysis. You get minus IR because you actually do get an electric field in a resistor. Think back to our Drude model discussion. And then you go through these highly conductive wires, and there's no resistance in this wire. So you don't really get a term from there. Right? There's no field inside that wire. See, that's all you have for E dot dl. Okay? But now, according to Faraday, the right side is not zero. We're creating a back EMF. We're creating a non-conservative field that's equal to d phi b dt. And you know from our discussion of inductors, d phi b dt is the same as L di dt. Right? Calling it the inductance L is just our way of not having to calculate the exact magnetic field in the geometry every time. Right? We know that the current and the magnetic field are proportional, so we just call it L di dt. So this is the proper equation. Okay? This, you could say, is like Kirchhoff's delta V's. And if you do, I will yell at you, because it's not Kirchhoff's delta V's. This is Faraday's E dot dl's. Right? And this is Faraday's d phi b dt. This is Faraday's flux. And you can see why it's tempting to use Kirchhoff's analysis, because all we do is bring this over here, and we get the EMF minus I times R minus L di dt equals 0. This is our differential equation that we would use to solve for the current as a function of time. And you can see it looks just like what we got with Kirchhoff's loop rule. EMF minus IR minus L di dt equals 0. Problem is, this one is for the wrong reason. And this one is for the right reason. It's because of Faraday's law. So, surprisingly, most books really either they choose not to discuss this or they don't understand it. I don't know. A lot of books will have a teeny little caveat that doesn't make a lot of sense when they present it, when they literally say the potential drop for Kirchhoff's loop rule for the inductor is minus L di dt. So the book I usually use says Kirchhoff's rules were developed for circuits with steady currents, but they can also be applied to a circuit in which the current is changing if we imagine them to represent the circuit at one instant in time. No, they can't. Okay, so if the current is at one instant in time, it's not changing and you lose your whole inductive effect. So really, there's really no justification. I've read another book that says, well, you can do it as long as you imagine that the current is changing very slowly. Well, if the current's changing very slowly, then there's really no back EMF. Right? You're taking the limit where this doesn't happen at all. So what's interesting is usually when something gives you the right answer for kind of the wrong reason, it's usually because you've made an approximation. That would be the case where the current is changing slowly. This isn't really an approximation. This is just wrong. It just happens to come out right, but not really for a good reason, right? This is really what you should do. Now, I don't want to get in trouble with the physics community, so in the rest of the videos, I'm just going to say I applied Kirchhoff's loop rule. Okay, so this is the only video where we're going to talk about this. Right? Everything else, it's just Kirchhoff's loop rule. It'll match your book. Everybody will be happy. Let's put one of these inductors into a circuit. That would be called an LR circuit. An LR circuit is just a circuit with an inductor and a resistor in it. So let's draw one here with a battery. Battery's making an EMF. And kind of like the capacitor, the RC circuits, we want to put a switch in it so that we can have time equals 0, where we can turn things on and off, you know. And then come down and have our resistor R and have our inductor L. And then finish off the circuit like that. Okay, so what do? Well, we apply Kirchhoff's loop rule. That should work. So to apply Kirchhoff's loop rule, we define the current. I'm going to start writing small i's for current now. I'm tired of the capital I. That just means current. And we say we always want to go clockwise when we apply the loop rule, just to be consistent. So you can say, I'm going to start here. And if I'm a test charge moving across this battery, that's going to be plus E, EMF, because I'm going from the low potential to high potential. And I move around, I'm moving with the current across a resistor, that's a potential drop, so it's minus IR. All right. And let's see, now I'm going through an inductor. Okay, now let's see, if the current is this way through the inductor, we know that the inductor, due to Lenz's law, always opposes any change. So if the current were to change, this would be a back EMF. We've talked about how inductors make back EMFs, and the EMF we know is L, the inductance, times di dt. So when you're going with the current past an inductor, it's minus L di dt. So we have that drop, and then we're back where we started, okay, equals 0. Go around the loop, it equals 0. So here is an equation where we need to solve for I, and it's another differential equation. We have I, current as a function of time, and we have the derivative, di dt. And solving for these is always a matter of just using the right tricks. So here, let's divide by R. And using the right tricks is a matter of experience. Minus I minus L over R di dt equals 0. So when you take differential equations, you're really just learning tricks, more or less. Well, there's some math in there too, but you're also learning all the tricks. If you've never had differential equations, the next few units will be useful. I'm going to teach you some of the differential equations tricks. If you've had them, you may just stop here and say you know the solution. I don't know. Okay, so the trick in this case is to substitute x equals, and we're going to make this our variable, the EMF over R minus I. So we substitute in, that'll just become x, but then we have to deal with di dt. So when you look at this, if you were to calculate dx di, it would be minus 1. Right? Dx di, the derivative of that with respect to I is 0, derivative of that with respect to I is minus 1. So if dx di is minus 1, then dx equals minus di. If you bring it back around, you'll just get dx is minus di. So if we make that substitution, we can rewrite this thing as here is x. And so x is EMF over R minus I, and then minus L over R. And then this is di dt. Well, if we want to change that to x, there's actually a negative sign. It has to get changed, and it just becomes dx dt. Equal 0. All right, so that substitution just makes it a little bit easier to deal with, because now we can use our trick we used when we were doing the capacitor differential equations. We bring this over here, and we bring the x over the dx. Right? So x over dx bring this term over here and divide through by the dx equals minus, because we brought it over there, it became minus, oh, sorry. Let's not do that. Let's do the correct thing. We want to bring this term over here and say it's dx over x, it's all over there, equals minus r over L dt. There we go. That's what we want to do. See, I forgot the tricks. Okay, and then now we integrate both sides. Right, so integrate. Here we're integrating with respect to x. Here we're integrating with respect to time. And this is when we have to think about our initial conditions. This is why we have the switch here. So we say, actually, the switch is open like this, and you close at t equals 0. So we're going to see what the behavior is starting at time 0 up to some time t. What's it doing? T seconds after time equals 0. And we know that x, whatever this x is, it's going to start at x naught. And we're trying to see what happens when it goes to x. So we set up that integral very similar to the capacitance equations. And these are the boundary conditions assuming x equals x naught at t equals 0. So now we just need to integrate. We take our integral, and integral of dx over x is natural log of x evaluated from x naught to x. And the other side, the integral of negative r over L dt is just minus r over L t. Right? Yeah, evaluated from 0 to t. So this becomes the natural log of x over x naught. The natural log of x minus natural log of x naught is natural log of x over x naught, and this becomes minus r over L t. And then we take the exponential of both sides. E to the natural log of something is a something, so this is x over x naught equals e to the minus r over L t. And let's see, we could even go one more step and write it in the form you would normally see it. X equals x naught e to the minus r over L t. So that is the solution for x, whatever x was. X was the EMF minus I over R. So now let's go and get back from x naught and x to real things. So let's see, at t equals 0, let's think about the real circuit. Let me look at it again real quick. The real circuit at t equals 0, we said we close it at t equals 0. And actually the current right at t equals 0 is going to also be 0. It takes a while for the current to get going in the circuit. So at t equals 0, I equals 0. So that tells us what x naught is. If x is the EMF minus I over R, I'm sorry, if x is the EMF over R minus I, then x naught would be the EMF over R minus nothing. Right? So that x naught is just the EMF over R. You can see that's actually the current that you would get if you had no inductor in there. So now we plug that in to here, and we plug in for x. So x is the EMF over R minus I equals x naught is the EMF over R e to the minus R over L t. And then you solve for I. So you bring I over here, you bring this over here, you divide through by the EMF over R, and you get that I equals the EMF over R times, it looks like this is over here, 1 minus e to the minus R over L t. So the current as a function of time is an exponential. In this case, it's a thing that grows exponentially to a saturated value, not exponential growth, but exponential growth. So let's take a look then at what it looks like. Here's time. Here's time equals 0. Here is the current. And if you plot a function like this, it starts out at 0 because e to the 0 is 1. So it's 1 minus 1 is 0. So it starts out at 0, and it goes up, and it kind of saturates to some value. And at time equals infinity, this basically just becomes a constant. This thing goes to 0, and it goes with a constant EMF over R. So that's the behavior. Now, let's see if it makes sense. Let's go back to the circuit and see if that's what we think would happen. Well, when you close the switch, the current is 0, but it starts to grow very fast. The di dt is very big, right, when you close the circuit. So since the di dt is big, the dB dt is big, you have a big changing magnetic field, so the back EMF is really big. When you first close the switch, not the circuit, when you close the switch, all your EMF drop is all across the inductor, and none of it is across the resistor, because the current's 0. There's no drop here. All the drop is here. And then, as the current builds, you start to get some of your drop here, and you start to build up a magnetic field here, and it slows down, doesn't change as much. And when you reach steady state, you have a constant current, constant magnetic field, no back EMF, and then all your drop is here. So your potential drop starts here, and it transitions to here, following this equation. So that's the basic behavior of the LR circuit. We have our nice B field in our inductor. Now let's discharge the RL. So let's look at the circuit again. It was like this. The battery caused current to flow. We reached a steady state where there's nice current going through the inductor. We have a nice B field now inside the inductor, but it's constant. So there's no back EMF. All the potential drop is across the resistor, and everyone is happy. Now, if we open the switch like this, this is no longer powering this current. You got to have the battery doing it because we're losing energy here. The current is flowing through the resistor. So this will affect the circuit, but it makes a lot more sense to analyze it if you have a loop. So usually you draw another line like this, and the switch can go between the battery and just having a closed loop like that. So this is what we're doing now. We still use Kirchhoff. We still think of the current going this way. We're going to analyze it this way. We're going to write essentially the same Kirchhoff loop rule, just without the EMF. So this is how we discharge the RL. And of course, discharge is not the right word. That's the word when you're using a capacitor, because you're taking the charge off the capacitor plates. For an inductor, I don't really know what the word is. There really isn't a word. You're turning the field off. I'm gonna create the word. You're discombobulating. There you go. We're going to discombobulate the RL. It's all okay, and it's got a B in it. So there you go. Okay, so to discombobulate it, we're going to apply the Kirchhoff rule, like we just said. We're going to say minus IR because we're going clockwise around the loop, and minus L di dt because we know that's what an inductor does. It has a back EMF equals 0. And now we're back to our differential equation tricks that do not require substitutions. Let's see, we're going to bring this over here, and we're going to get di over I on one side, and then we're going to end up with minus R over L dt on the other side. And we integrate both sides like that. So integrate this side, integrate that side. And now we need these boundary conditions. We need to say that we had, at time t equals 0 is when we flip the switch. So at time t equals 0, we had some current. Okay? We had a current I naught. So we would say the time, at 0 we flip the switch, and we want to know what's happening at some later time t. And at time t equals 0, we had I naught, some initial current, and we just want to know what happens to that current. So it goes from I naught down to some current I, like that. All right, well, now we just have to integrate both sides. So this, we've done that integral a few times. It's the natural log of I evaluated from I naught to I. And this one is minus R over LT, evaluated from 0 to t. And we've seen this before. This is the natural log of I over I naught equals minus R over LT. And then we take e to this and e to this, and you get that I equals I naught. So this becomes I over I naught. Take it to the other side, equals e, I naught e to the minus R over LT. So you find that it undergoes basic exponential decay. If we were to plot versus time and plot I, it starts at some value I naught, and it just makes its way to 0. That value I naught, you can look at it and realize, oh, well, when I first flipped it, the current was running as though the inductor weren't even there. All this potential drop was gone, so the current is just the EMF over R. I naught is the battery's EMF over R. So as the current dies away, the magnetic field goes away, there's no dissipation of the resistor, and it just goes, everything goes to 0.